I have never heard that. And maybe that's not even a song. Maybe it's just time a little bit.
Yeah, no, that is a song.
Okay.
Oops, I did it again.
Oh my goodness.
I don't know anything after that.
Now you make me a little ashamed. All right. We're going to talk about transient circuits. I have first a transient, well, not transients actually, that's not the goal. It's to get to the AC circuits. So we already talked about transient RC circuits. We already did the calculation that, for capacitor, since C is Q over V, that's the definition. Then if we just solve that for Q and take the derivative of both sides, we have current is equal to capacitance times dV dt, where V is the voltage across the capacitor.
Right.
So we already saw that. And then we said, okay, so if we use that equation, we can analyze a transient circuit, a circuit that has a switch that's going to change it from one state to another and evaluate what's going to happen. And we worked out that our when I scaled things, obviously I didn't quite scale it right. I didn't realize this V was on a different line. But we came up with the equation for the voltage across the capacitor is the voltage it had at the instant you flip the switch minus the voltage it will have after it's been in that position for a very long time, e to the minus t over tau, plus the voltage it has during rest time, where tau is RC. And likewise, the current is the current it will have immediately after you flip the switch. Remember, the current for a capacitor can jump. So whereas the V0 is the voltage just before you flip it, because it's going to stay the same just after, the current has to be calculated right after you flip the switch based on what the voltage in the rest of the circuit is.
Right.
And then the current will have after infinite time, and so on. And so here are graphs of what it looks like if you're going from an uncharged state to a charged state or vice versa. And actually this is voltage is discharging, current is increasing on the graph shown. So we've already gone through that. We did those calculations. So now we're going to go to, we're going to see how we could do this with an inductor, but we're going to the AC circuit, which is what we're doing in lab today. But we're doing a cut down version, as I said in the message I sent out yesterday, because we haven't had a lecture on that. We're going to have some lecture on it before lab today, but that's not much preparation. So
we're not doing all of lab today then?
We're doing a cut down version. That's right. You apparently didn't see my message.
Apparently not.
I specified what we would be doing. You can just go to Moodle. I posted on Moodle, and then it sends you an email from Moodle.
Okay.
So this is a series RLC circuit. You can have a parallel RLC circuit, or you can have a complicated RLC circuit. But we're only looking at the series case. So we have a resistor. This L, that's the symbol we use for an inductor. And C for capacitor. So that little thing looks like a spring. Usually you don't see loops. Usually it's just... But you can see by the similarity between resistor and an inductor, you have to be careful that resistors have sharp angles.
Right.
And inductors, one side has to be loopy.
Right.
All right, so for a resistor, we know Ohm's law. Voltage is IR. Very simple relationship between voltage and current. For the capacitor, we had worked out a not so difficult current to C dV dt. And here I was specific that V is the voltage across the capacitor because you might have voltage somewhere else in the circuit. You have to be clear on what voltage you're talking about. Well, what about the inductor? Oh, actually, I first do.
Could you scroll just a little bit?
Yeah.
Okay, so it's dVdt over dt. Okay.
Yeah, you should have that written down from previous
I'm
iteration.
sure I do, but
Yeah, just staying in sequence. So let's look at our first case here. This is an AC circuit with no inductor. So it's just an RC AC circuit. So in this case, if I have a current that is sinusoidal, so current is I max sine omega t, then what is the voltage across the resistor?
so the voltage across the resistor, let's say that's V equals IR, right?
Right. And so the voltage is going to be, if I plug that in, I max R sine of omega t.
And omega is the.
So omega is the angular frequency. So if this is 60 hertz, if F is 60 hertz,
Then
omega is 2 pi F.
That's right. I did write that down somewhere yesterday.
So I can calculate my I max times R as the maximum voltage I'll have across the resistor, and it's going to be a sinusoidal fluctuation. But what about for the capacitor? What's the voltage for the capacitor?
Voltage for capacitor is complicated.
So what's the equation you just wrote down?
IT equals C dVc T over dt.
Okay, so there I substitute for I, it's I max sine omega t.
Oh, they are equal.
Well, I is I.
Oh, right.
So what's in blue is not the same as what's in red, because the red one had an R.
That's not
Yes,
the same.
okay.
But
The current through the resistor, current through the capacitor, because they're in series, those are the same.
right.
Okay, so how do we solve for VC in this equation?
I have to integrate.
Have to separate variables and integrate. So I need to add in an extra page here. Page manipulate. I'll probably have to do this a number of times because I didn't add any pages beforehand. So I'm going to separate variables. So I have dVc is equal to Imax over C sine of omega t dt. I moved the Imax over C so they'd be together. Well, now we're going to do, we separate variables, we integrate the two independently. So I independently integrate them. What's the integral of dVc? VC. So I'm going to have for my answer VC equals, and on this side, what's the integral of sine of omega t?
That's going to be omega negative omega cosine omega t. Yes, over omega.
So VC, and of course there could be a plus constant with the VC, but we're just saying that plus constant is 0 here. So VC is equal to Imax cosine of omega t, put a minus out front, over C omega. Now let's compare that to
limits.
I didn't put limits on here. That's why I said there is technically a plus C to be involved here.
Okay.
But we are just saying that plus C is 0.
All right.
Now I have cosine of omega t and minus cosine of omega t to be exact. Well, minus cosine omega t is not the same as sine omega t. If I were to plot these, I would have, here's a sine of omega t. And so this is time equals 0 here.
Yeah.
Well, cosine would be 1, so minus cosine is going to go like this. These are supposed to be on top of each other. So when one is at 0, the other's at its peak. And so it turns out that minus cosine of omega t is just the sine wave shifted by 90 degrees. But which way is it shifted?
Because it's negative, I'm going to assume to the left.
Well, that was supposed to be just a span. That wasn't actually supposed to be a negative sign. But
Oh, no. I was talking about the negative cosine. Because the negative
okay.
Because the cosine is negative, I'm assuming it's to the left.
So if I wanted to make sine wave, the red wave, match the blue wave, do I have to add 90 degrees or subtract 90 degrees? If I add 9 degrees, no, I actually have to subtract. Because if I subtract 9 degrees, then the time is going to have to go over, so I'm 9 degrees further.
Is there a way you can show me that algebraically?
I'm hoping I'm right here. First of all, I'm rethinking myself before I go on. You have sine of 0 degrees equals 0. Cosine of 90 degrees equals 1.
No. 0.
0, right. 0 is what I was shooting for. I wrote the number wrong, not the angle wrong. So cosine of 90 degrees is...
Okay. So by subtracting 90 degrees and switching from cosine to sine, you get the same thing.
But we have to be careful. Cosine of 90 degrees is 0 and going down. Right?
What do you mean?
Cosine of at 90, okay, cosine of 0 is 1.
Yes.
Cosine of 90 is 0, but it's going down, so cosine of 180
so
would be minus.
Negative.
Yeah.
Okay, yeah.
So that's going down, where sine of 90 degrees is going up.
Right.
So if I did sine of, if I did cosine of minus 90 degrees, that's equal to 0, but that's going to be going up. So sine of 0 degrees is the same as cosine of minus 90 degrees. Or, yeah. Okay, so now I'm getting myself wrapped in circles. Sine of 0 is, cosine of minus 90. And that means that minus cosine means that you have to add or subtract 180 degrees. Right, because cosine of theta is equal to minus cosine of theta plus 180. Yeah. So the minus cosine of 90 degrees is equal to sine of 0 degrees. So now what I want to do is I want to say, if I have an angle of theta plus, I need to have an angle of theta plus, right, to make them so they change together.
Right.
And so this is equal to minus cosine of 0 plus 90 degrees is this, or bring it over. I did pluses. If I subtract 90 from both sides, I would have cosine of omega t is sine of theta minus 90 degrees. Is that what I said the first time?
Yes, because theta minus 90 degrees. Yes.
So I went through probably 5 times longer than is necessary to show this, but I had to think it through for myself while I was working here.
Yeah.
Because, you just get used to things and you forget
Right.
why.
Plus, personally, I don't like taking you at your work.
That's good. That's the way you should be for all of your teachers, by the way, not just me.
Yeah. Some of them I just accept it because it's like organic chemistry.
All right. So what we have here, I'm going to come up to here and rewrite what we just worked out. VC equals
5x.
So this here, I put it in parentheses because it serves the same function as R did.
It does?
Well, I times R, I times 1 over omega C.
Okay.
So it must have the same units as R. Must be ohms, right? Because it's still voltage equals I max times this times sine, which doesn't have any angle to it, or any units to it. So 1 over omega C must have units of ohms, and we actually give this an abbreviation. We call it X sub C, and we call it the reactance. So what's the maximum voltage we'll have across the capacitor? It's either I max times XC or I max over omega C. Either one would be a correct state.
Right.
So we can calculate the maximum voltage across the capacitor using this XC. But notice that XC depends on the frequency, on omega. So if omega is small, what does that make XC?
If omega is small?
Yeah.
Should make XC pretty big.
Right. And so for this circuit, if we had a current source, right, this is shown as a voltage source, right, 10 volts. But if we had a current source, so it was the same I max constantly, the voltage across the capacitor would rise as you get to lower frequencies. And the voltage across the capacitor would drop if you went to higher and higher frequencies. Now, because it's a voltage supply, it's going to still have that function, but it will be more complicated because the current is going to change as you change the frequency because of the increased what we call reactance. Now, the second thing of note here is that sine of omega t minus 90 degrees. That minus 90 degrees means that the voltage across the capacitor is 90 degrees, quote, out of phase with the voltage across the resistor. They don't reach their peaks at the same time. They reach their peaks 90 degrees out of phase with each other.
Yes.
Now let's talk about the why so this can make some sense instead of, wow, that's what the math says. What does a capacitor do?
Capacitor stores energy.
Stores energy in the form of a charge separation, not a charge, or an electric field.
Is there really a difference between charge and charge separation?
Yes, because it doesn't store charge. The net charge in the capacitor remains zero.
Because one side's positive, one side's negative.
Right.
Okay.
So it's not storing the charge, but it's storing the separation of it.
Right.
Okay, so we're storing energy. We store energy by having current flow to it. So if current is flowing to it, the energy stored is getting bigger. And then if current flows away, the energy stored drops. So now when we have the circuit, as the current is flowing to it, it stores more and more energy. So the rate at which the energy storage is changing depends on the current, but it's storing energy. So if you have current flowing to it, you're just adding to it. If the current stops flowing, it's going to then give that energy back and create a current flowing out.
That makes sense.
And so that's why it's out of phase, because you put energy in and it stores it. And then you don't put energy in and it gives it back.
Right.
So when you're giving nothing to it, it's giving something to you.
So does that mean if a current stops and the capacitor starts keeping the current going, will the current gradually weaken more and more?
Right. As the capacitor's energy drops, the current will drop. Because it's basically acting like a temporary battery, right? It's storing energy and then giving it back.
Theoretically, then, is it possible to have a circuit run by a capacitor alone perpetually? Theoretically.
Theoretically, if you had a capacitor and an inductor and zero resistance, and they're completely isolated, so nothing else could be, draining off, then you could have energy go back and forth between the capacitor and inductor and go forever oscillating.
Okay.
But you can't have zero resistance. And you can't have no parasitics.
Kind of like nuclear fission.
No, nuclear fission's real.
Yeah, but is it?
I mean, that's why Hiroshima got destroyed.
Wait, is it fission? Oh, I'm sorry. I'm talking fusion.
Fusion. Well, nuclear fusion is also very real. And
yeah.
You can definitely get more out of a nuclear fusion reactor than the energy you put in to make it go. But the problem is they make big explosions. The sun continues to operate just fine because gravity is controlling things.
Right.
We as humans haven't developed something quite so sophisticated.
Which, if we could, wow.
Yeah. I just read an article this morning about a potential. Now to the inductor. The inductor, the last thing we did in class, after all else failed, was we worked this out, except for, of course, we did it without calculus. Right? So
that was wonderful.
That's not wonderful. That's the hard way.
Really? So, without calculus is the hard way?
Well, it just makes more sense to me with the calculus.
Oh, of course it makes
so
sense.
Here's Faraday's real law of induction. It's a derivative.
Right.
And so for the capacitor, for an inductor, you have a coil. And so you make a magnetic field in that coil that's given by mu naught capital N over the length. Remember, N is the number of loops. And L is the length of the, we can call it a coil, but now we call it an inductor. Yes, that's why I said we called it the coil. Now we'll call it an inductor, but it's the same thing.
So on power lines, those big metal towers that are on like the side of the highways and stuff.
Mm-hmm.
I'm not talking the wooden post stuff. No, I'm talking about the big metal ones that like go up hundreds of feet, and then they have these big cylindrical shaped things that are kind of like wide and then narrow, wide again, kind of like kind of like a coil, but
they're not. Those are ceramic insulators.
That's just okay. Look, you kind of feel like an idiot now.
No. And of course, I say they're not. Maybe who knows? Maybe I don't know everything.
I mean,
things like
I would think you wouldn't.
I don't have anything here that has one. Okay. But here you go. This here is called a choke.
This one.
Yeah.
Okay.
And what is it?
I'm assuming a resistor. No.
It's coil.
It's a coil. It's an inductor.
It's not connected into the circuit. These things, you can slide them sometimes. They're clamped on the outside of the cable.
Okay.
So it's a coil around the cable.
So what does it do then?
What does it do? It does what we're seeing right here. It does what an inductor does, except for you're not connecting it to anything. So an inductor.
I must be not understanding.
Well, let's go on and you'll see.
Okay.
An inductor responds to a changing magnetic flux.
Okay.
And so if you have a current going through, in that case, you have a current going through the coil that creates the magnetic field that you can see the equation for the magnetic field I explicitly put in right here. This is the magnetic field.
Okay.
And
number of coils. What's I?
I is the current, and it's a function of time. So I put parenthesis T to say that that's current as a function of time.
Well, what's the L stand for?
Current through the inductor.
Okay, so
L is the symbol for inductor.
Uh,
So script L is length, so we can keep capital L inductance and lowercase l length separate.
Okay, so script L is the length. I is simply the current through the inductor.
Yes.
And there's number of currents, and mu naught is a constant.
And it's number of loops. And mu naught is constant, yeah.
Okay.
Now, the area, just like this, the area isn't going to change. It's just a constant. It's the cross-sectional area, the area of the circle if you have a circle. And so that was supposed to be a theta, and it's a 0 instead. I just fixed it.
It is
well,
important.
What is theta? Right. Actually, no, it is supposed to be cosine of 0. I was right. It's cosine 0 because it's cosine of the angle between the magnetic field and the area. And the angle between the magnetic field and the area is 0.
Right.
And so that's just a 1.
Yeah.
And so it turns out that the voltage across the inductor is minus this stuff here, which is physical parameters, mu aught, the number of turns, the length of it, the area of your loops, times the derivative of current with respect to time. And so what we do, the minus sign gets gobbled up in our definition of what direction is the positive and negative for the inductor. So the minus sign just disappeared because of our definition of which side we're calling positive.
Right.
We do it like this, just like we did for a resistor.
Okay.
And that's where the minus sign went, was in that definition. And then L is this stuff here. So the stuff that we worked out last class period,
Yeah.
this right here, that was the inductance.
Okay, hold on. Okay, see that. So L is essentially N times the NBA is L.
Not NBA. L is mu aught n squared A over.
Right. But if you do a little bit of algebra, if you do a little bit of algebra, you can see.
Yes, I see what you're saying. I see what you're saying. What you're saying is if I take this equation right here,
Yeah.
and I recognize that the derivative is only affecting I,
Right.
then n times mu aught n, you can't just say B because the B depends on I.
Oh, okay. That makes sense.
Yeah, because I was like, wait, I am getting to the same thing. Yes, because I was part of the B.
Okay.
So this here is the inductance L. Now, if you calculate the units, I don't know, it's something crazy. The units for this are Henrys. H for Henry. I call him Hanks because I pretend I'm friends with Henry, which is his last name. And it's probably pronounced Henry or something like that too. Not to be confused with ornery.
Can we please have a physics unit called Audrey?
That's actually a good request right there. So what's the upshot of this? The upshot of this is that, notice this was dependent on the magnetic field.
Right.
The inductor stored energy in the form of a magnetic field.
Okay. So capacitor in charge separation, inductor magnetic field.
Yeah, or capacitor electric field, inductor magnetic field is the easier way to remember because then you're both fields.
That's true.
Now, what is this doing? This here?
That is a great question. I've been so curious.
What is it doing? If you have a change in magnetic field, it will respond by absorbing some energy and dampening that change. What causes a change in magnetic field if you have a surge in current?
Magnetic field is going to increase.
Right, because you have current going through a wire, it's going to create a magnetic field.
Okay. So essentially, this is a circuit protector.
Yes.
What's this thing?
That's a transformer.
That's a transformer.
And it should have a surge protector, but like I said, if you unplug it, you're going to have a surge.
Right.
And so to help protect you.
So an inductor is a surge protector.
Hmm?
An inductor is just a surge protector.
In this application.
In this capacity.
Yeah. It's not technically an inductor because it's not wired in.
Oh, an inductor has to be wired in?
Yeah. So the current goes through it.
So then.
And I'm pretty sure these are not wired in, like I said. I'm pretty sure these are just clamped on around it. And it says on here, EML suppressor. Electromagnetic, I don't know what L is.
EML suppressor.
I'm actually giving you time to look this up because I'm curious.
I couldn't find it.
Did you get anything?
It just says a bunch of stuff about. It just says email. Email.
That's E,
Suppressor.
the letter E, the letter M, the letter L.
Yeah.
I'm doing it too.
Yeah, I'm super curious now. Like, why use the letter L?
People who watch my videos, why do they do it? There's somebody who, I don't know, I think he just wants me to like his Facebook channel. Every lecture, he's like, great lecture. Can we be YouTube friends?
Why?
I'm just posting my lecture. I'm not here to.
Not here to make friends.
Well,
a little bit.
Anyhow, you didn't find anything?
My computer kind of.
Yeah, my web browser is slowly coming to life. I believe it will start up soon. Okay, well, let's get back to this.
I will continue looking at
Okay. So remember we had our definition of the positive side with respect to current. With the definition, if the current is increasing, then you're going to have the positive side on one side. If the current is decreasing, the positive side on the other, because the DLDT changes sign.
Wait, hold on. I thought that the inductor had a positive and negative side like the resistor.
We're marking it like that, yes.
Okay.
We're marking it like that. But it turns out that when the current is increasing, we have a positive value for that voltage. But when the current is decreasing, you have a negative value for this value. So you mark this side as positive and this side as negative, but that's a negative value.
So they switch.
Yeah. So if you have, this is the positive side of minus 10, it's actually the negative side.
Right.
And so that's what this is pointing out. If the current is increasing and going to the right, then it's positive. If it's decreasing going to the right, then it's negative. So once again, you can immediately see, hey, I think we're going to have another one of those phase shift relationships between voltage and current.
Mm-hmm.
Because if the current is constant, what's the voltage? Just look at this equation. If I is constant, voltage is?
Also constant.
Derivative of constant is constant, but what do we call that constant?
Oh, it's zero.
Yeah.
For some reason, my computer is dying. Like, it's just talking.
Ferrite cores are generally used on HDMI cables with high AWG ratings. Such as 28 or 30 AWG. That's the American something gauge, the size of the wire. The bigger the gauge, the smaller the wire. High AWG rated cables are cheaper to produce and generally have little or no shielding at all. It is likely that you will, this is written by some random person, find short length cables with ferrite on them. Ferrites are a way to reduce high frequency noise in the cable. They are an alternative method to reduce EMI, RF, etc., to simply produce a well-shielded HDMI cable. So Ferrite Core apparently is another name for that.
Okay.
And Wikipedia says, in electronics, a ferrite core is a type of magnet core made of ferrite on which the windings of electric transformers or other wound components such as inductors are formed. It is used to provide high magnetic permeability. Maybe I was wrong. Maybe it's just a piece of iron in a loop around it.
Oh.
I thought it was a bunch of loops. Maybe it's just a single iron.
Would that be as effective? I mean,
Well,
because doesn't the number of loops increase? Because it looks
no,
like
actually, I think it would, because the magnet. I was thinking about the directionality and being a little confused when I was talking. Because if I have a current going through the wire like this, the magnet field goes like this, right?
Right.
Well, if I put an iron thing around that, then the iron is in the direction of the magnetic field. And so the iron is going to act like a magnet,
right.
That's going around like this. Yeah, so it's north to south, continuous circle.
Mm-hmm.
And if you have a surge in current, it's going to try to make that magnet field stronger. And the iron, you have to actually do work on the iron to make things align to make it stronger. And so that's I think, how it's doing it. And of course, you actually.
Man, now I really want to like find one of these and like make a massive surge and like have shavings around it.
Okay.
Probably a bad idea though.
The most important outcome of what we've done, it is important to see things like, well, when current is constant, voltage is zero, just like with the capacitor, when the voltage was constant, the current was zero.
Yes.
Which also gives you a reason to say, it's got to have a 90-degree phase shift. But we have this relationship that we can now use in a circuit, just like we did the relationship between voltage and current in a capacitor. What's different here? With the capacitor, it was I is equal to C dV dt. Now it's V is equal to L di dt. So it's the opposite one being in the derivative, which is going to help us explain why the phase shift is 90 degrees in the opposite direction, because we're taking derivative of the opposite variable.
What does the C stand for in that?
C was capacitance.
Capacitance. Okay.
So if I have an AC circuit with a resistor and inductor, and I put that same current through, what's the voltage through each item? Well, what's the voltage for the resistor again?
Voltage for the resistor. IR. T. That's going to be I max sine omega T.
Okay. Now for the inductor,
So that's going to be L di. Wait, what? Huh?
that's a DI. It just got a sweep on there. So L d I max sine omega t dt.
So then L is the same as R. Well, L.
Well,
is
that's
the same.
L times I max, because it's a constant. What's the derivative of sine of omega t?
Negative cosine omega T over omega. Oh wait, the derivative.
It's positive. You did the integral, right? Yeah. It's positive and it's times omega.
Yes.
Or to write it the same way we did last time, equals I max, parenthesis, omega capital L, positive cosine of omega t, or I max
I max R. No, not R.
x sub L sine of omega t plus 90 degrees. So this was omega t plus 90 degrees because it didn't have the minus sign. Right? When we did the capacitor, we had the minus cosine of omega t. Now we have plus cosine of omega t, so that's why it's plus 90 degrees instead of minus 90 degrees. 180 degrees different between plus and minus cosine.
Why do I get the feeling that the reading is more for me than anybody else in perusal?
It's for everyone. The problem is I'm behind.
Well, no. Like the reading that was due yesterday, both had these XL and XC equations.
Right, and we're going to cover this in lab today as well.
Oh, so these equations will be covered by that as well. Okay.
That will be covered in the lab.
Okay.
Not as in depth.
Right. But here, these exist.
Yeah, exactly. Alrighty. So our outcome here.
That's just our outcomes.
Our outcome here was V inductor is equal to I max XL sine of omega t plus 90 degrees, where XL is equal to omega c. So now notice XL, the reactance of an inductor, increases with frequency, whereas XC, the reactance of a capacitor, decreases with frequency. So what was reactance? Reactance was like resistance. Why do we use the term resistance? When I was a young kid, I asked my uncle. I was really confused. Of course, I didn't even know what resistance was, much less anything else. They talked about resistance and reactance and impedance, and I was like, what? So here's the breakdown. Resistance, that is when you try to push charge through It takes away energy.
Right.
Reactance, when you try to push charge through, it reacts by storing energy.
Okay.
So it didn't absorb it. The resistance absorbs energy.
Right.
The reactor stores it and will give it back.
Okay.
So that's why we use reactance versus resistance.
Okay.
And then we have the word impedance. Both of those are going to make it so we have to push the charge through.
It sounds like
And so impedance is the combination of resistance and reactance.
okay, so
But because of those angles, the plus 90 degrees, the minus 90 degrees for the capacitor, we actually have to calculate it differently. The impedance, I'm just going to write this here. The impedance is equal to square root of R squared plus parenthesis XL minus XC quantity squared. That's the impedance. What does that look like? It looks like the Pythagorean theorem because it is the Pythagorean theorem. Because XL and XC are 90 degrees away from R, then we just add them like vectors. We call them phase vectors or phasors for short. And so we're actually just taking this part, and this part. We add these two parts because they're anti-parallel, so that's why there's a minus sign between them. So we're adding the vertical parts, and then we take the hypotenuse. So the Z there is the impedance.
okay. So resistor simply makes you put more work in.
A resistor is you're gonna have to put in energy to make the charge flow.
Put it in there and you put it through.
And absorb the energy.
Right. Reactance, you push it through and it stores energy.
Yeah. So you still have to put in energy, but it stores it instead of getting rid of it.
Right. Impedance, you have to put.
Well, impedance is a combination of the two.
Right. Impedance, you still have to put in the work, but it'll store the.
It might store some of it. It depends on the XL, XC versus the R.
Okay.
Right. Because if XL equals XC, well, then you're not storing the energy.
Okay. So the further apart they are, the more it'll store.
Yeah.
Okay.
Okay. So, given this circuit, now we have the Rlc Series Circuit. What are the voltages through each element if I have that same current? Well, I don't have to go back and reinvent the wheel. I have done all of these. I have the voltage across the resistor is I max R sine of omega t. The voltage across the capacitor is I max X sub capacitor sine of omega t minus 90 degrees. And voltage across the inductor is I max X inductor sine of omega t plus 90 degrees.
Why is voltage across the reactant of I max R sine omega t instead of just IRT?
Well, it is IR,
Well, yeah.
but I is a function of sine omega t.
Yes.
So I plugged this in, right? I plugged I is equal to I max sine omega t.
Okay.
So those are the voltages as a function of time for each one. Now in lab today, you're going to observe these and you're going to measure to see if those angles are really plus and minus 90 degrees. Hot tip, one of them should be, one of them won't be. Why? Because inductors are made by wrapping wire in a loop. The resistance to that wire is not zero. And so the inductor actually has some resistance in it, which is going to make it so the voltage that you measure across the inductor is going to be an inductive part plus a resistance part. And that's going to change the net angle. If you had a perfect inductor, no resistance in the wires, and this is important, no iron core. They put iron cores in them because it really raises the inductance by changing mu odds, and mu that's maybe 1,000 times bigger.
Right.
But at the same time, that's going to put in an absorption of energy, which to us looks like a resistance. And so a real inductor is not actually going to be 90 degrees out of phase with the resistor because it has some energy loss, some resistive, either real resistance from the wires or apparent resistance from the energy absorbed in the iron core.
So is that why in the reading I asked a question about this? I noticed that the graphs, they weren't uniform, I guess is the best way to say it. So like you were talking about earlier, how it was literally just a 90-degree shift to make them line up. But in the graph, like the sinusoidal wave was kind of angled a little bit. So like one side was up top here and then kind of got closer and closer to the bottom.
It should, and I'll have to look at your comment. I'll have to look at your comment, look at the graph you're referring to, because it shouldn't do that.
Maybe I was just not looking at it.
Maybe your screen was at an angle.
Maybe, but I mean, it kind of looked like the top side, like when they crossed, and then they angled out of it, and then they kind of got closer and closer again, and then they crossed. So kind of like.
Well, let's just do it. I know my electric, so let's look.
Okay, so
Just pull through though. Sure.